And we are very happy to give this tutorial because we have been working now on vision-based autonomous navigation of drones, and more recently also agile navigation for 17 years. So I think it's good to share also what we, the research journey, but not only, especially to give you a tutorial about how to basically go from state estimation to planning and control. We will pass towards NPC, then learning-based control, SLAM, also reinforcement learning-based SLAM, foundation models, and then learning in the real world, and very finally also on multi-agent systems. So I will first talk for about 25 minutes. We'll take some questions. I will be followed by my postdoc, Rudolf, who actually did this PhD with Moritz Dill. He is the guy behind Akados, the main solver of MPC. And then we'll be followed by Ismail, who will talk about foundation models and training in the real world. So first, a little bit of a motivation. So what are we trying to achieve in my lab? In my lab, we want to understand what it takes to fly autonomous drones better than human pilots. Why? Because we want to push the limits on vision-based navigation. And we hope that the results that we achieve will be then transferable to other domains like autonomous cars, autonomous legged robots, humanoids, and space robots. What you see here is not an autonomous drone. It's a drone operated by an expert human pilot. How do human pilots navigate drones? Vision-based. They put a camera on board the drone that transmits the images to goggles, and then the brain operates everything. At the beginning, when we started this journey, we thought that in order to beat human pilots, you needed to be faster, but actually we were wrong because the human brain is very slow. It takes a quarter of a second to analyze the images, while our algorithms are 10 times as fast. So the reasons why still humans are better than machines is not because they're faster, but because they can make better decisions in complex situations. Why do we want to fly drones fast? Well, because we want to increase the productivity, so the utility of the drone. So a multi-rotor can only fly for half an hour, more or less. So if you want to fly longer distances, you need to fly faster. And actually, this is also supported by this study, which was published in these papers, where you can see the maximum range that a multi-rotor drone can reach as a function of the ground speed. And what you can see is that the range increases. This is the maximum range you can achieve before depleting the batteries. But there exists an optimal speed, because if you fly faster than the optimal speed, then it's no longer convenient to fly fast, because then you start encountering more rotor drag, and so you draw more energy from the batteries. Now, when you look at this plot, we started wondering, okay, but where are current commercial drone companies situated on this plot? So we picked Skydio, Flyability, DJI, which are the world-leading companies in the things they do, and we realized they are not flying yet at the optimal speed. But we know one day all commercial drones will be flying at the optimal speed in order to maximize their utility. Why? Why are they not flying at the optimal speed? Because there are several challenges when you fly vision-based. But in order to understand what these challenges are, we need to understand how drones are controlled normally. Well, they are controlled with the usual perception, planning, and control architecture, which has been used for more than 40 years in robotics, from vacuum cleaning robots to autonomous cars. Perception does estimation and builds a map of the environment. Planning computes an optimal trajectory, and control computes the rotor speeds. Now, this architecture is very successful, so why changing anything about it? Well, the problem is it starts to be a little brittle, fragile, when you fly faster vision-based, because you may encounter motion blur. You will have a quick rotation of the camera, which will cause, for example, overexposure or underexposure of the image. So both motion blur and over or underexposure will cause the loss of feature tracks. Those feature tracks that you need for state estimation, SLAM. But there is another problem when you fly, compared, for example, to ground robots, is that if you want to start applying, foundation models, when you need to collect data from a huge amount of conditions, so both from low altitude, high altitude, and different angles of flight. There is an additional problem when you actually fly drones agilely. The drone behaves as a soft robot. What? It's a soft robot? Yes, it is, because to isolate the vibrations from the motors to the cameras, you need to add dampers. And these dampers can cause, under the high accelerations that the drone experiences, errors in state estimation of up to 2 meters. So what we started doing, starting from 10 years ago, is try to combine the traditional perception, planning, and control architecture with the deep models. Sometimes replacing some of those modules, sometimes going end-to-end, some other times instead, for example, by learning a residual that we cannot explain with first principle models. The problem, though, when you start mixing model-based approaches with deep models is how do you train these models, with or without supervisions? And where do you get the data? Well, in most of the research we've done, actually, we collected most of the data in simulation with minimal fine-tuning in the real world. But then the problem is, how do you address the simulation to reality gap? And this is a problem that we are facing every day in our community, not just for flying robots, for manipulation, space robots, and so on. Now, at my lab, rather than working abstractly, we picked 3 tasks in order to measure the performance of our fast-flying drones with respect to human pilots. So these are not the most useful for humankind, but they are the most useful for us researchers to basically measure our progress. So we picked drone acrobatics, navigation in the wild, which means in unknown environments like forests, and then drone racing. But in order to work on these tasks, we also had to build a very agile drone. So in 2017, we started a collaboration with Marvin Schepper. He is the 5-time Swiss champion of drone racing. He was 15 years old at the time. I'll introduce Marvin in a moment. And then we built Swift, the drone that you see here. It's about 20 centimeters in diameter. It has very powerful motors that can accelerate the drone from 0 to 100 kilometers per hour in 0.7 seconds. Formula One takes 2.6 seconds. You experience up to 5 Gs of acceleration, which is what you experience on a roller coaster. And then for the brain, we use NVIDIA Jetson. Initially, we used the TX2. Now we are using Orin. And for the eyes, we had a lot of success with the inter-real sense cameras because we could crash this drone at 100 kilometers per hour, and very rarely we broke the sensor. So to be honest, I was very happy about that. Now, a few videos before going into the details. So this is old work from 2020 and 21, where we demonstrated that thanks to machine learning approaches and the combination of model-based and deep models, we were able to fly very agilely, and for the first time outside of our lab. So here you see on the left the drone performing acrobatic maneuvers, and on the right the drone flying up to 40 kilometers per hour in an unknown forest doing slalom. We also compared against the best model-based approaches, and we found that these policies were actually flying up to twice the speed of model-based approaches. Why? Because they turned out to be much more robust to sensor noise. So like, for example, left to right stereo matching, and also different lighting conditions. The interesting thing, though, is that in order to train these models, we needed a lot of data. So we didn't collect the data in the real world because it's too difficult and it's also dangerous, but we collected data in simulation. Why? Because simulation is fast, it's cheap, and it's very, very safe. So on the left, you see Gazebo, the simulator we used in 2020 to train the policy doing acrobatic maneuvers. And on the right, you see Flightmare, which was built based on Unreal Engine and Unity. That is much more sophisticated simulator. It's now our state-of-the-art simulator. It allows you to download, for example, 3D models from Unity or Unreal Engine, for example, here at Forest, and then train with domain randomization. These policies were trained in the arc of a night, so 5 to 8 hours. However, the problem is that when you train policies in simulation, there is no guarantee that they will work in the real world. And so here, the key enabler was that we didn't train on raw image pixels, but we trained on an intermediate representation from the pixels. The intermediate representation depends on the task that you want to solve. For acrobatic maneuvers, it was optical flow vectors. For navigation in the wild, it was depth maps. So this means that depending on the task you want to solve, there exists an optimal intermediate representation. However, these policies were trained with imitation learning, which means that you have to have a demonstrator in order to train the policies. And you can never outperform the demonstrator. And that's the reason why in 2017, we started also to work in parallel on drone racing. Why? Because in drone racing, we soon realized that there is not a demonstrator. You also don't want to take the best human as a demonstrator because you want to find out whether you can train a policy to be better than the best human on the planet. So what is drone racing? How does it work? Why did we pick drone racing as a benchmark to push the limits in vision-based navigation? Well, everything started with the IROS Drone Racing Challenge in 2016. In 2017, we won the challenge. No, in 2018 in Madrid, going at 3 kilometers per hour. Now we can fly at over 100 kilometers per hour. And in 2017, we also started a collaboration with the 15-year-old boy, Marvin, that was coming to our arena with his father, because of course he was a minor. Let me introduce you to Marvin. And there should be sound here. So here you can see how drone racing works. The pilot wears goggles.
Get ready on the top in less than 5. Beep!
So as you can see in drone racing, there is no time for thinking. It's basically a sport where, you have to be very quick at making decisions. And you can see that Marvin always tries to cut the edges of the gates. And in the end, you always end up crashing because you don't want to end with 0 speed, right? But with the maximum possible speed. So how does drone racing work? So in drone racing, basically, you need to pass through a sequence of gates in a given order. The order of the gates is given by the organizers. It's very important to make it clear to everyone. It's an overfitting task. So the training and testing environment are the same. Even human pilots get access to the racing track 2 weeks before the race. And in the US, for example, they even get a simulator that they can use at home to train before going to the televised competition. So what do you want to do in drone racing? From an optimal control point of view, what you want to do is to find the control inputs U of t that minimize the flight time through a sequence of gates in a given order. So you want to minimize this integral, subject to physical and systems constraint. But most importantly, because you're flying vision-based with egocentric vision, you want to take the perception constraint into account. That's what makes everything difficult. Why? Because when you fly vision-based, you start to encounter motion blur, quick rotation of the cameras that cause underexposure and overexposure of the camera, which can cause a loss of visual tracks. So now you need to generate trajectories that facilitate the perception task. So it's very difficult to solve this optimization. That's the reason why, when we started working on drone racing, we said, let's decouple perception and control. Let's assume that perception is solved, which of course is not. So let's assume that we delegate the localization stuff to a motion capture system. Then we will remove it later. So what is then the problem? In this case, the problem seems easier because you know the track. So you can, in principle, use all the model that you have at your disposal and try to generate the so-called time-optimal trajectory. So we came up with an algorithm that we published at Science Robotics that not only computes the optimal control inputs that minimize the lap time according to the current model of the drone, but it also gives us a lower bound. So you know that you cannot go lower than the lap time. So that's very cool. Now, in principle, you could use this algorithm to navigate the drone. The only problem is that if there is a minimal disturbance, and the racing is actually a task where there is a lot of disturbances because there is hysteresis. So every time you fly, your turbulences will affect your behavior 10 meters apart. So you'll never be able to reproduce the same trajectory. So if you wanted to apply this algorithm in the real world, you need to replan very fast. And with this algorithm, it wasn't possible because the optimization time would take around 1 hour. That's why another PhD student, so that was the work by Philip Thorne, who should be in the audience today. That's why another PhD student, Angel Romero, started working on trying to enable replanning. And here the idea of Angel was the following. Instead of starting with this, solving this complex optimization problem, let's assume a simple problem. So, and then let's let MPCC to try to find a faster trajectory. Here, the idea is to bootstrap the system with, for example, straight line trajectories connecting all the centers of the gates, and then let model predictive contouring control to find the optimal trajectory. In model predictive contouring control, what you're trying to do is that you try to minimize the error from a reference track while at the same time maximizing the progress towards the next gate. Well, what Angel found is that thanks to this algorithm, the replanning took only 2 milliseconds. So we went from 1 hour to 2 milliseconds, so which is faster than real time. And we were able to do things like this. For example, Angel put a fan, and then it was blowing wind at 70 kilometers per hour, and the drone was able to actually withstand the gate, the wind. It even showed that you could actually possibly move the gates. Here is Angel wearing a helmet for his own safety. He's moving the gate, and it's showing that the drone is replanning very fast. But when we then perform against the best human pilots, we realized that we were still below the performance of human pilot because of unmodeled effects. What are these unmodeled effects? Well, I told you that the main problem is actually perception. Let's try to understand what the problem of perception is. So here you see the footage of our AI racing drone that in the end challenged the world champion pilots. And the way it works is that it uses a combination of VIO, so visual inertial odometry, and also map-based localization. So it detects the gates using a neural network. Then it detects the 4 corners of the gates. It applies PNP, perspective from endpoints, and then it triangulates the position of itself. Well, when you use a camera to estimate your position, you suffer from the parallax problem, which means that your error is always quadratic with the distance from the gates. So it shrinks or it grows. What is not modeled here is actually the errors of state estimation that are caused by motion blur or overexposure and underexposure of the camera. Those are very difficult to model. That's why, after insisting for 6 years on optimal control, another PhD student, Yunlong Song, actually started working on an alternative approach. in parallel to the optimal control approaches. And this one was based on reinforcement learning. So here, instead of using a classic controller, we delegate the controller task to a neural network, a two-layer MLP, which is trained in simulation mostly with model-free deep reinforcement learning, trying to maximize this reward function, which is composed of different terms. Here, I'm going to show you the time lapse of the training. To speed up the training, we simulated 100 drones and learned to basically first hover, then fly, and then fly superhuman. The optimization now takes around 10 minutes, but if you bootstrap it, now it takes less than a minute. And here you can see that at the beginning, the drone learns to hover over a gate, then they start to pass through the gates, and then they start actually racing. At the end, they start racing almost as the best human champions. What we found out was actually interesting, that if you plot the reward function as a function of the iterations, of the time step of the training, you find that if you stop the training after 10% of the iterations, and you deploy the policy, you would be surprised how fast the drone is. So for people who are not in this field, they would say, oh, wow, it's amazing. It flies like one of the best pilots. But actually, it doesn't fly like a world champion. It still takes 90% of the time steps to learn to fly as a superhuman champion. And this is actually interesting because we found an analogy also with how humans learn to walk and then run and eventually run a sprint. It takes around 1 year to learn to walk, but it takes many more years to learn to run, and it takes even longer, to some people never, to actually run a sprint in the Olympic Games. So after working on this problem for about 7 years, in June 2022, we felt confident enough to invite to Zurich not just Marvin, the Swiss champion, but also the world champion pilots at the time. One was Alex Vanover, and the other one was Thomas Bidmatta. They were the two world champions of the two main drone racing leagues. And we invited them for a week to Zurich because we wanted to give them time to practice on the racing track, like in normal competitive competitions. And we gave them the same hardware used by Swift, by the AI drone. So the drones of the human and of the AI were identical. So the same mass, the same aerodynamics, the same camera, the same field of view, the same frame rate. The only difference was one was autonomous with an onboard computer, and the other one basically relied on off-board compute, the brain. Here is the footage of the race. There should be sound. So one of the two is the human, Alex Vanover, and the other one is the AI. So Swift won, otherwise I wouldn't be here telling you the story. It won with 15 out of 25 races, so 60% of the races. When it didn't win, it was because there was an in-flight collision with the pilots. And it reported also the fastest lap time, which was 0.5 seconds ahead of Alex Vanover, which was the best of the pilots. Here you can see the distribution. By the way, we recorded all the trajectories, and they were put open source in 2023 when we published the Nature paper. So we released the 1,200 trajectories. You can train them to train your foundation model if you want. And what you see on the left is the lap time distribution of Swift, and the other three in orange is Alex Vanover, which was the best of the champions, followed by Bidmatta, followed by Marvin. And you can see that there is a distribution between Marvin, the Swiss local champion, and the world champion. So it's good to also always try to approach world champion, because then you can really see if the AI is doing better. But this time, it was not enough to train in simulation. Why? Because now you're really trying to shoot for the top, okay? So simulation doesn't capture all the idiosyncrasies of the real world. All this hysteresis effect that I was telling you, the fact also that we have this residual perception model, the residual perception that is due to the fact that we have dampers that cause errors in estimation of up to 2 meters due to the compression of the dampers, the motion blur, overexposure, underexposure of the camera. For doing this, to capture these effects, what we needed to do was to collect data also in the real world. So the first takeaway, the first key enabler of this research is the following. When we train the policy in simulation and we deploy it in the real world, we are not able to outperform the world champion. We are just a little bit below the world champion because of the residual models of perception and aerodynamics. However, we can collect data in the real world. We collected 3 laps in the real world, so about 300 meters of trajectory. Then we modeled the discrepancy between the trajectory predicted in the real world, in simulation, the one executed in the real world using a Gaussian process. We add this Gaussian process to our simulator. Then we fine-tune the policy in this improved simulator. Now the fine-tuning is much faster. And finally, we deployed it fully vision-based on the platform. And that's when we beat the world champion. So this definitely was the key trick that allowed basically outperforming the world champion. This sim-to-real to sim-to-real has also been exploited very recently, a few weeks ago, by Sony AI Zurich to beat some of the best players of table tennis in the world. So what they did here is also the following. They first trained the policy in simulation, then they collected the real-world data. They used this to actually capture the residual models. They added them to their simulator and defined the policy, and that's when they started building the pilots. So that was takeaway number one. The second takeaway is we wanted to understand why reinforcement learning beat optimal control. So we worked for 6 years on optimal control. We published amazing papers at Transactions of Robotics, Science Robotics, RAL, but eventually reinforcement learning won. Why was it the case? And actually, we realized that the reason why RL won was because we were pushing the platform to the limits of physics, to the limits of handling. And that's when things start to actually become very difficult to model. So the problem is that optimal control always decomposes the problem into planning and control. And this separation causes basically the planning to bias the final control maneuvers that the controller might discover. Running out of battery. So, okay. Okay. In contrast, also RL has another advantage. It can directly optimize a non-differentiable objective function, which is, for example, directed uptime, while optimal control always requires a continuous differentiable objective. In addition, RL can benefit from domain randomization, which allows, basically in simulation, to expose the policies to all the features that you want your controller eventually to become invariant to. Now I'm going to delve more in detail on the simulation part, because this is something we really talk about, but I wanted to talk about in this tutorial because when you fly these safety critical machines, you crash a lot. So we crashed more than 1,000 times in the past 6 years. But of course, we don't want to crash. So how do we manage to go from simulation to the real world without destroying, without consuming too much money? So, by the way, the details are also given in this Science Robotics paper, Agilicious, which released open source and open hardware, most of the things that we are talking about today. So, for training our RL, we use very fast and parallelizable models that include a quadratic thrust torque propeller model, and this basically runs at 20,000 times faster than real time. Now, you may wonder, what about accuracy? Well, actually, what we found out is that's actually one of the key findings of this research that we are very happy about, is that you don't need a very accurate simulator to train with reinforcement learning, provided that you do good domain randomization. Thanks to domain randomization of the inertia, mass, aerodynamic forces, and control delays, we were able to actually account for all the discrepancies between simulation and the real world. But now, for validation, we use a more realistic simulator. We have 2 validation stages before we fly the policy vision-based in the actual arena 100 kilometers per hour, because we want to minimize costs. So the first is, when we validate it in a photorealistic simulator so that we can also benchmark the perception tasks, the perception models. It's so realistic that we actually also simulate motion blur and vignetting. Let me show you our simulator. So these are a digital twin of our arena. We rented the arena from one of the hangars in the Zurich military airport. This digital twin was built by Hexagon. So it has tens of millions of points with RGB information. It's so accurate that it's difficult to distinguish reality from simulated. So let me show you 2 videos. One of them is simulated, the other one is real. Video 1. Video 2. Who thinks that the first one was a real world? Who thinks the second one is real world? Okay, there is a 50-50. Actually, the first one is real world, because what we are not simulating is the shadow of the drone on the floor. That's a key difference. But this is to tell you how accurate it is. And we use Habitat 2 in order to do the rendering super fast. But remember, we are using this not for training, but for validation. Not only do we do photorealism for validation, but we also run the same software, the same ROS nodes on the simulated drone as on the real drone. This is very, very important. And then we use very accurate drone models for the sensors and the dynamics, again, for validation. What are these drone models? For example, we have a very accurate aerodynamic model that incorporates both blade element momentum theory models based on first principle models, and then residuals that were captured with more polynomials or neural networks. And these residuals allow to account for the 60% of aerodynamic forces and torques that we cannot model with the first principles. These vortices that you see here in this picture. We also use a gray box model, and we also use a one-time custom model of the battery. This is very important for validation because when you go at high accelerations, you consume all of a sudden a lot of battery. The other validation is very important. It's part of Agilicious. It's hardware-in-the-loop simulation. What you see in the background is our drone flying actually in our arena, but it sees virtual reality images. So virtual reality for drones. So this allows us to basically simulate an almost unlimited amount of real-world environment to test our perception models, while we actually sense the actual physics and aerodynamics in the real world. This is all available on Agilicious. Now, we learned a lot with this research. And we also learned, especially, that visual inertia estimation is not solved when you fly fast. You see, a lot of these data sets today are saturated, HIT, UROC, TUMAR-GBD, but there are data sets, for example, like our UZH-FPV data set, which is not saturated, and still the majority of SLAM algorithm cannot get to the top. Same for Tartan version 2, the data sets, for example. VIO is still very brittle, very fragile. You know that NASA landed Ingenuity on Mars in 2021, and Ingenuity reports a drift of 1%, which is pretty good. Now, if you run the best VIO on a racing drone at 100 kilometers per hour, you realize that the drift is not 1%, it's 20%. So the drift is also a function of the speed at which you're flying. And this we didn't know, because it depends on the apparent motion, which depends on the relative distance and speed from the structure. And what causes this drift? Motion blur and the quick rotations of the camera that cause underexposure and overexposure. Here you can see that what happens because of motion blur is that after a while you lose feature tracks. The only way to recover is to use an IMU, but VO approaches alone are not enough. But what if I told you that there is a way to make VO, standard VO or VSLAM methods to work also at these speeds? What is the key? We need to remember that all these VO, VSLAM algorithms have around 50 to 100 thresholds that most of us never touch. The fast corner detection threshold, the ransack thresholds, the KLT pyramid levels, the KLT patch. There are so many that most of us really never bother about touching them. The problem is that these algorithms are tuned by experts, by us, researchers, engineers, on pre-recorded data sets, and they're never changed in the real world, unless you have an heuristic. But this heuristic is made by us humans. So what this means is that when you deploy a system in the real world, it's not optimized for the real world because it was only optimized to be fine-tuned on those specific data sets. There is no guarantee that they will give the best performance in the real world. What would be the ideal VO VSLAM algorithm? The ideal VO VSLAM should be one that has an agent on board that for every image tells you, I've seen this kind of scene before, this would be the right combination of VO VSLAM parameters. What if you could actually train such an agent, and then at deployment time, every time you see an image, you map it to a set of parameters for your favorite VSLAM VO algorithm? So you don't need to turn to deep SLAM VO methods. I was last year working at JPL. They don't like deep models. They like to work with the models like VSLAM that they understand. So we came up with this idea that we first published at DCCV 2024. It's now, we have a follow-up version on arXiv, which consists in using reinforcement learning to train an agent that then at deployment time will take an image and will map this image into the ideal set of parameters for your favorite VO or VSLAM algorithm. So now the agent predicts actions that are not control commands, but they can be the fast corner detection, threshold, KLT patch size, ransack threshold, feature distribution, number of keyframes. And the observation to the agents are images. Well, training from images is too costly, so we train on an embedding of 128 features. And now let me show you some qualitative results. On the left, you see a traditional VO that basically breaks because of motion blur. And on the right, you see our system, the same VO, which now has the agent at deployment time, inference is fast, it's 1 millisecond, that does not break. We didn't change any algorithm. We didn't use any deep model. We just have an agent that maps an image to to thresholds. We did this for SBO, we did this for DSO or SLAM. This is to show you that the approach generally can be used for any SLAM algorithm.
本演讲实录已收录至雷锋网 ICRA 2026深度专区，现已全面上线。专区不仅全面收录了重磅论文的工程化解读、专家前沿演讲，更将持续更新前方记者的第一手会议动态。扫描下方二维码或进入雷锋网 ICRA 专区即可查看。